AI Model, Patient Care in the Hospital. By Pradeep K. Suri, author, researcher, consultant, and AI/ML architect. Deep Neural Network, DNN, for hospital patient care. This document provides insights into how a deep neural network, DNN, is used to classify hospital patients into risk categories, low, medium, high, based on health-related input features. One management point of view. From a hospital management perspective, this DNN model is valuable for patient risk classification, identifying high-risk patients early for better resource allocation. Decision support system, assisting doctors and hospital staff in prioritizing patient care. Optimized healthcare workflow, efficiently managing hospital resources, such as ICU beds, medical staff, and emergency care. Data-driven decision-making, using AI to improve healthcare outcomes and reduce hospital readmissions. Regulatory compliance and reporting, ensuring accurate risk assessment for medical audits and compliance. 2 Hidden layers data processing. Hidden layers perform feature transformation and nonlinear learning. Input layer, accepts patient health indicators, example previous hospital visits, BMI, blood pressure, oxygen levels. Hidden layer 1, performs the first transformation using weighted summation Z1 equals W1x plus B1 Z_1 equals W_1x plus B_1 Z1 equals W1x plus B1. The stacked bar chart visualizes the workload of doctors based on patient risk levels, using concepts from statistics and data visualization. It categorizes patients into low risk, medium risk, and high risk, represented by green, orange, and red bars, respectively. The total height of each bar represents the total number of patients per doctor, making it easy to compare workloads. This falls under descriptive statistics, using frequency distribution to analyze patient counts. Additionally, the visualization technique applies graph theory and proportional summation, ensuring clear data representation. From a mathematical perspective, the chart also incorporates arithmetic, summation of patients, ratios, and proportions to maintain balance in risk distribution. If predictive analysis were involved, probability theory, like Bayesian models, could help estimate patient risk shifts over time. Furthermore, if patient data were stored in a structured format, linear algebra could be used for matrix-based computations. Overall, this visualization bridges multiple mathematical domains, making it a powerful tool for medical data analysis. And applies activation function A1 equals F, Z1, A_1 equals F, Z_1, A1 equals F, Z1. The given formula A equals F, Z, represents a functional relationship between 2 variables, where A is dependent on Z. This falls under the branch of mathematical analysis, specifically functional analysis and calculus. In this context, F, Z, denotes a function applied to Z, which could represent transformations, differentiable mappings, or integral operations. Such equations are common in differential equations, where dependent variables change concerning independent inputs, and in optimization theory, where functions define constraints or objective functions. Additionally, this formula aligns with algebra, particularly abstract algebra and linear algebra, if the function f represents a transformation such as a matrix operation. In applied mathematics, it is frequently used in probability and statistics when z represents a stochastic variable, and a is its expected transformation. This type of function also appears in machine learning, where activation functions map inputs to outputs in neural networks. Thus, the formula bridges multiple mathematical domains, including analysis, algebra, and applied mathematics. Hidden layer 2 and 3, extract complex relationships between features to refine risk predictions. Output layer, uses a softmax activation function to classify the patient into low, medium, or high risk. Purpose of hidden layers. Learn patterns from medical history and vitals. Transform raw input into a meaningful risk score. Handle nonlinearity in health conditions, making predictions more accurate. 3 AI/ML developer point of view. From an AI/ML development standpoint, this model involves data pre-processing, handling missing data, normalizing vitals, and encoding categorical values. Model training, using gradient descent and backpropagation to optimize weights. Hyperparameter tuning, adjusting the number of layers, neurons, learning rate, and activation functions to improve accuracy. Model evaluation, testing with cross-validation, confusion matrix, precision recall analysis. Deployment and integration, deploying the trained model into a hospital management system for real-time predictions. Key AI/ML concepts used. Probability and statistics, used for model evaluation and risk scoring. Linear algebra, essential for matrix operations in weight calculations. Calculus, backpropagation relies on gradient descent, which uses differentiation. Softmax activation function, ensures the final output is a probability distribution. For AI architect point of view. An AI architect focuses on designing the scalable, efficient, and explainable AI system. System scalability, deploying the model on cloud-based healthcare systems for real-time predictions. Model interpretability, ensuring AI decisions are explainable to doctors and policymakers. Ethical and regulatory considerations, complying with HIPAA, GDPR, and medical ethics. Integration with hospital IT systems, connecting the model with electronic health records, AIR, and IoT medical devices. Computational efficiency, optimizing inference speed for real-time patient monitoring. Architectural decisions. Choose between on-premises deployment versus cloud-based AI, example AWS, Azure, GCP. Implement model versioning, monitoring, and retraining pipelines. Use secure API layers to integrate with hospital management systems. 5. Patient point of view. From a patient's perspective, the DNN model significantly improves healthcare services by faster diagnosis. AI models assist doctors in early detection of critical conditions, reducing waiting times. Personalized treatment plans, AI-driven insights help in tailoring treatment plans specific to a patient's condition. Reduced hospital readmission rates, predictive analysis helps in preventing avoidable complications. Better communication with doctors, AI-generated risk assessments enable more data-driven discussions between doctors and patients. Improved health outcomes, timely and accurate predictions allow preventive care measures, improving overall patient health. 6. Hospital point of view. From a hospital administration perspective, this AI model contributes to optimized resource allocation, helps in efficient utilization of hospital beds, ICUs, ventilators, and medical staff. Enhanced emergency preparedness, AI predictions assist hospitals in planning for emergency cases and patient surges. Improved hospital ratings, better patient care leads to higher hospital reputation and accreditation scores. Cost savings, reducing unnecessary treatments, hospital readmissions, and optimizing doctor-patient interaction saves operational costs. Data-driven hospital management, AI-generated insights provide accurate reporting for insurance claims, audits, and medical research. Conclusion. This DNN for hospital patient care serves as a decision support tool for doctors, management, AI developers, hospital administration, and patients. It optimizes healthcare services by predicting patient risk levels, ultimately improving patient outcomes and resource allocation. List of output reports and graphs from data processing. The Deep Neural Network, DNN, for hospital patient care generates various reports and graphical representations to provide meaningful insights. Below is a structured list. 1. Output reports. 1.1 Patient Risk Classification Report. Lists patient ID, name, age, gender, health score, and risk category, low, medium, high. Includes prediction confidence score for each risk category. 1.2 Daily/monthly patient admissions report. Number of patients admitted per day/month categorized by risk level. Helps in resource planning for ICUs and general wards. 1.3 ICU and emergency department utilization report. Total ICU admissions versus general admissions. Highlights percentage of ICU patients classified as high risk by AI. 1.4 Patient Health Progress Report. Compares historical versus current health indicators for individual patients. Tracks improvements or deteriorations over time. 1.5 Hospital Resource Utilization Report. Beds, ventilators, doctors, and nurse availability versus patient demand. AI-based prediction for the next 30 days based on patient flow trends. 1.6 Doctor Workload and Efficiency Report. Average patient load per doctor. Number of high-risk cases handled by each doctor. 1.7 Readmission Risk Analysis Report. Identifies patients most likely to be readmitted within 30 days. AI-based suggestions to reduce readmissions. 1.8 Cost Analysis and Financial Report. Total hospital costs per patient based on risk category. Comparison of projected versus actual patient care costs. 1.9 Mortality Risk Prediction Report. AI-based early warning system for critically ill patients. Helps doctors take preventive measures in time. 1.10 Patient Satisfaction and Outcome Report. Surveys and feedback analytics mapped with AI-generated risk levels. Identifies correlation between AI predictions and patient outcomes. 2 Graphs and visualizations. 2.1 Patient Risk Distribution Graph, bar chart. X-axis, risk categories, low, medium, high. Y-axis, number of patients. 2.2 Time series graph of patient admissions. X-axis, dates. Y-axis, number of admissions. Shows trends in patient flow over time. 2.3 Hospital Resource Utilization, pie chart. Segments, beds, ICU beds, ventilators, doctors, nurses. Displays real-time hospital capacity usage. 2.4 Doctor workload versus patient risk level, stacked bar chart. X-axis, doctor name. Y-axis, number of patients, stacked by risk level. 2.5 Patient readmission risk over time, line chart. X-axis, time. Y-axis, percentage of high-risk readmissions. 2.6 ICU versus general ward admissions, histogram. X-axis, number of days. Y-axis, number of patients. 2 bars for each day, ICU patients versus general patients. 2.7 Cost versus risk level graph, scatter plot. X-axis, risk level, low, medium, high. Y-axis, average cost per patient. 2.8 Survival rate vs. Early diagnosis graph, box plot. Compares mortality rates for early diagnosed versus late diagnosed patients. 2.9 AI model confidence score distribution, histogram. Shows how confident the AI is in its predictions across different risk levels. 2.10 Overall hospital performance score, radar chart. Tracks AI efficiency in reducing readmissions, optimizing ICU usage, and improving patient care. Conclusion. These reports and graphs help hospital administrators, doctors, and AI engineers understand patient risk levels, manage resources efficiently, and improve hospital performance. Sample output. Detailed explanation of the image. The image is a stacked bar chart that visualizes the workload of different doctors based on the risk levels of their patients. The chart has a dark background and uses color-coded bars to represent 3 levels of patient risk. Key features of the chart. 1. Title. The title of the chart is Doctor Workload versus Patient Risk Level, Pradeep K. Suri, author, researcher, consultant, and AI/ML architect. This suggests that visualization is based on data related to patient care and workload distribution among doctors. 2. X-axis, doctor names. The X-axis represents different doctors who are handling patients. The doctors shown in the chart are Dr. A, Dr. B, Dr. C, Dr. D, Drive E. Each doctor has a stacked bar above their name, representing their total number of patients categorized by risk levels. 3. Y-axis, number of patients. The Y-axis represents the total number of patients handled by each doctor. The bars are stacked, meaning that each section of the bar adds up to the total number of patients seen by that doctor. 4. Risk levels, color-coded stacks. Each doctor's workload is divided into 3 patient risk levels, represented by different colors. Green, low-risk patients with minimal health issues. Orange, medium-risk patients with moderate health concerns. Red, high-risk patients requiring urgent or intensive care. The colors are arranged from bottom to top in ascending risk order. 5. Legend, risk level categories. The legend on the right side explains the meaning of each color. Red, high-risk patients. Orange, medium-risk patients. Green, low-risk patients. Observations from the chart. Dr. C and Dr. D have the highest number of patients. Their bars are the tallest, indicating that they handle a significant patient load. They have a balanced distribution of low, medium, and high-risk patients. Dr. A has the fewest patients. The bar height for Dr. A is the shortest, meaning they see fewer patients than the others. However, their patients are mainly low and medium risk, with very few high-risk cases. Dr. B and Dr. E have similar workloads. Both doctors have nearly identical bar heights. They have a moderate number of high-risk patients, making their workload slightly more demanding. High-risk patients are fewer across all doctors. The red section in all bars is relatively small, suggesting that most patients fall into low and medium risk categories. Conclusion. The chart effectively shows how patient risk levels vary across different doctors. The stacked bar format provides a clear comparison of workload distribution. The dark theme enhances visibility, making the colors stand out. This type of visualization can be useful for hospital management to balance doctor workloads and allocate resources efficiently. For a deep neural network, DNN, to generate such an output, a stacked bar chart for doctor workload versus patient risk level, the input must be structured in a tabular format with relevant features. The dataset should include hospital department-wise patient data with key attributes that influence workload and risk categorization. Required input features for DNN processing, table format. Doctor name, department, patient ID, age, diagnosis, risk level, low/medium/high, consultation time, minutes, number of visits, severity score, numeric. Dr. A cardiology P00165, heart issue high 4538.5. Dr. B neurology P00250, stroke medium 326.2. Dr. C orthopedics P00340, fracture low 213.0. Dr. D general med P00472, diabetes high 649.1. Drive E pediatrics P00510, fever low 1512.5. Explanation of input features for DNN. 1. Doctor name, identifies the doctor treating the patient. 2. Department, specifies the hospital department, example cardiology, neurology. 3. Patient ID, unique identifier for tracking patient data. 4. Age, helps assess risk level, elderly patients may have higher risks. 5. Diagnosis, medical condition affecting patient risk classification. 6. Risk level, label, low, medium, high, for supervised learning and model training. 7. Consultation time, total time spent with the patient, indicating workload. 8. Number of visits, frequency of patient consultations with the doctor. 9. Severity score, a computed numerical score based on multiple factors, example symptoms, vitals. DNN processing workflow. 1. Data pre-processing, convert categorical values, doctor name, department, risk level, into numerical form using one-hot encoding. 2. Feature engineering, generate derived features, example weighted workload per doctor. 3. Model training, train a DNN on labeled data to predict risk levels and analyze workload distribution. 4. Visualization, convert model predictions into a stacked bar chart showing patient risk distribution per doctor. This structured input allows the DNN model to learn patterns in doctor workload and patient risk levels across different hospital departments. Thank you.